so what we're going to talk about today, sorry, I didn't know if you were exclaiming about something else. So yeah, today what we're going to talk about is the other part of virtual memory that's like in really clever, badass systems, but it's not in most modern operating systems. Windows tries to be slightly clever. Linux, I think, tries to be slightly clever, but most people are not very clever about this. And it actually has to do with page allocation. So we talk about page replacement, page eviction, and if you build a pure demand page system, you don't really ever care about page allocation because you basically give processes pages when they need them. And that's all you do. Okay? The operating system clearly requires some frames. We don't talk about this too much. And it's really weird because this is probably the level of indirection that is the worst and most difficult to understand in programming. People always talk about the things that really identify good programmers are an understanding of pointers and recursion, because both of those things are kinds of indirection that you need to understand more complex systems. So if you at least have a good grasp of pointers and recursion, then you're probably going to become a very good programmer. But the virtual memory system sucks. I mean, it's like so complex. And the kernel can't even really refer to physical page addresses in most places because it's program. It's not allowed to emit physical addresses. There are very few places where you can use physical addresses. One is like the interrupt descriptor table. I think the address for the start of the interrupt descriptor table actually has to be a physical address. So there's a few things like that, but most of the stuff on the computer system is actually virtual addresses. So you have to keep all this stuff in mind. Now, the reason why I'm mentioning that is because one place where physical addresses are often necessary is the buffers used by peripherals for reading and writing data. So if you are talking to the disk controller and you say, hey, disk controller, I want you to store data here, you give the disk controller, almost always you give it a physical address, not a virtual address. So the kernel has to be aware of physical addresses, and so it will set some frames aside because they're physical addresses that peripherals can write to. It tends to be a more limited address space. Some peripherals actually understand virtual addressing, but remember, this is on the other side of the MMU, so the peripheral's addresses aren't translated. It has to actually either do its own address translation or it just uses physical addresses. So this all dictates some details about where, what pages the kernel wants to reserve for itself. That's the real reason why I'm kind of mentioning that stuff. Yes?
Are IOMMUs kind of changing that, though?
Yes, I think they are, and I don't know enough to speak more specifically about it. But yes, it's starting to have a big effect on this kind of thing. What I suppose it means is that you can actually have your operating system become a little bit clever. But yeah, that's something I should probably do some research about and include in a subsequent iteration of this class is IOMMUs. Yeah. Okay. So basically anything that the kernel doesn't need for itself that sort of allows it to run the computer system properly can be allocated to processes, and the OS gets to make some decisions about it. So basically there's two things in this vein that the OS can control. One is how many processes are currently running. Again, we're taking a step back to sort of the batch-oriented processing systems of the past. Right now, in most of our operating systems that we use day to day, the user controls the degree of multiprogramming. Like, oh, I'm running too many programs, I'm going to kill some, I'm going to shut down programs. But also how many frames are allocated to each process. And notice that I say frames. So I may say that I have 5,000 pages that I would like to use. I have to do the math to figure out how many megabytes that would be. But, let's say I have 5,000 pages I'd like to use. But the operating system can say, well, I'm going to give you 40 frames to store those 5,000 pages in. So if your working set is within 40 frames, you're good. You won't have a whole bunch of page faulting. If your working set was 200 pages and you only had 40, then you'd have a lot of page faulting going on, and your system would be slower. So anyway, this is where the page allocation policy really fits into the picture. So this is what's saying how many frames should each process have, because the frames are a limited resource, And then as the system runs, clearly how many frames each process has will interact with the working set size of the processes, and that will have a profound impact on the overall system behavior. So we'll talk a little bit about this. Yeah, so the main goal, make sure everybody has enough frames. That's easy enough. What that really specifically means is really much more challenging. In general, we'd like to make sure that processes have the frames that they need. Again, if the working set of the process is relatively small, then we're okay, because they'll be able to have all the pages that they need loaded into the frames that they have, and everything will just go fine. Okay, so the reality, though, of course, is that we do expect page faults. Page faults aren't bad because, hey, we may have ready-to-run processes, and if a process page faults, then now it's blocked for a little while, and we can move it out of the way, and we can schedule other ready-to-run processes. So in a sense, page faulting isn't too bad a thing. It means that the program can actually be put aside, and we can let other programs run. Clearly, it is time that is lost, especially for the process that page faults. Okay, so it's going to slow down that process. But when we have a bunch of processes that want to run at any given time, this sort of helps reduce that number. Okay. Now, still, if you were, saying, well, does that mean that we want to have a lot of page faults? Not really. The less, the better. But if there is a small number of page faults occurring all the time, it's actually not all that bad. We have a little bit of additional overhead due to the interrupt handling and loading pages, so you have some pressure on the I/O subsystem and so forth. But that's okay. Typically, these things aren't 100% utilized anyway. Now, if we get to the point where the amount of I/O due to paging starts to, so basically what we do is we have a set of processes that could be ready to run, and the set of processes gets so small because they all end up blocked on the I/O subsystem because they're trying to load pages from the backing store, then we basically have a situation where the entire system performance really starts to degrade rapidly. And so we say that the system is thrashing. And again, this is one of those things where I think if you have a more historical perspective, i.e., you actually used systems with spinning magnetic disks at some point in your life and encountered this kind of behavior, then you would be very familiar with thrashing. Now we're getting to the point where, like I have a solid-state drive in my laptop. I don't know how hard it would be to get it to thrash, honestly, because I/O is pretty fast on a solid-state drive. But I also distinctly remember sitting in front of the computer that I'd carefully saved money to buy and put my 100-megabyte drive in it and all of that stuff, and I'd be running Windows and I'd be running too many programs, and the disk light would be consistently on, and the entire system is running very slowly. That's because it was thrashing. I had too many page faults occurring, so processes really weren't able to make progress. Okay? Now, I definitely do not have experience with what it would have been like for magnetic tapes to be whirring and trying to swap pages in and so forth. That must have been a real crazy experience. I actually have a friend that I'm going to see tomorrow, so maybe I'll ask him if he ever saw a system thrash on tape drives. He talked about the very first time he was working in a programming shop, and the first time that they got a hard disk delivered, and it was the size of a washing machine, and the platters could actually be swapped in and out, and they were this large, but they were really only about that wide, and so they would be able to trade them in and out of the hard disk drive. That was wild. I'm glad that's not my experience. Okay, so you can have individual processes page fault to the point that they start thrashing, but typically you see this on an entire operating system basis because of the kinds of things that we'll talk about momentarily. That typically our page allocation policies are global, our page replacement policies are global. So one process starts to thrash, everybody starts to thrash. Okay? All right, so yeah, thrashing occurs. Total number of frames that processes are using exceeds the number of frames available in the system. What we're saying again is that the working set size of all the processes is larger than the total number of frames that we have in the system. Okay, so yeah, a process generates a page fault. That evicts a page that some other process was actually using, and so we're going to get another page fault in the future. Okay, so it can occur unexpectedly. So this is a very simple example. We have an OS running 4 processes. It's got 20 physical page frames. Each process is has an address space that includes 10 pages, but its working set size is only 5 pages. Okay? Well, so we're fine. We don't have any thrashing here. In fact, we probably wouldn't have any faults except when a process's working set has a page leave and other page enter. Those would be the only situations where we get a fault, and that wouldn't be too bad. But if we had two processes start accessing all 10 of their pages, then their working set suddenly has grown from 5 pages to 10 pages. Now I need 30 frames to keep everybody happy. But the system only has 20. So now the I/O overhead skyrockets, and the CPU utilization will not be able to be maintained at 100% because the I/O is going to limit that. Okay, so yeah, and notice again, because we have sort of a global page pool, we'll talk about this in more detail. So in this scenario, you would see all the processes' page fault rates go up, even the ones only using 5 pages, because they would be swapped out. Okay, we'll talk about that in more detail. Okay, we've already introduced the notion of the working set when we talked about WS clock last time, so we won't talk about that. Degree of multiprogramming, number of processes, we introduced that in like week 1 or week 2. So in general, this is the kind of behavior that you observe. These are sort of experimentally derived graphs. I didn't take this from a research paper. I took it from the course textbook, and it's an approximate thing, but this is generally what you see. You add processes to the system, the CPU utilization increases to 100%. But at some point, if the processes are using a lot of memory, they're accessing a lot of memory, you will also see the page fault rate increase until it hits some point where suddenly the CPU utilization drops precipitously because the I/O system is fully maximally utilized. And that's where we say the system is thrashing. So is this directly related to the degree of multiprogramming? Probably not so much. It really is a combination of the number of processes and the number of pages in their working set. So perhaps this isn't an entirely accurate picture, but it's a pretty accurate picture. Okay. Hopefully you can look at this and eyeball it and say, okay, I can identify the ways in which this is not entirely precise, but it does approximate reality. Okay. Let's see. Yeah, so OSes that have, remember, we talked very briefly and then completely ignored them from that point forward, the notion of long-term and medium-term schedulers. We don't have long-term schedulers because if you had a long-term scheduler, what you would do is when the user clicked on some application and said, I want to run this, the OS would say, I'm sorry, I can't let you run this application yet because I have too many other things running. So that would be the goal of a long-term scheduler. So typically, we just say, sure, you can run your program. Okay, so medium-term scheduling would suspend processes temporarily if having them around was slowing everybody down. So we don't really have those things. Okay, so we already talked about that in the past. So we could actually build a medium-term scheduler that utilized the page fault rate to tell when do I need to suspend processes. And with the appropriate page allocation policies, you could actually say, this process is causing all the trouble. Now, if everything is global, then, like I said, all the processes are going to start to page fault, or many of them are going to start to page fault. So you couldn't necessarily use that to tell which processes to evict. But if you did start to see a page fault rate where you're like, okay, my CPU utilization, you could look at how often is the idle process running, or the idle kernel thread. Oh, it's running a lot. Well, then my page fault rate may be too high. I need to start suspending processes until the idle process is not really running very much. That would be an example of how you could do that. Okay? And so then you could just unsuspend those processes when the page fault rate goes down. Okay? This is if you have a medium-term scheduler. We generally don't anymore, which makes me a little sad because it would be a fun thing to try to create. Okay, so we just generally rely on the user. Okay? When I would see my computer system start to thrash, I would have to go shut things down. That generally is how we handle it. In fact, I had a meeting for a CS81 last week, and the person was talking to me about the thing that they wrote, and they said, I started to see my system thrash, so I had to stop my program because it wasn't behaving very well. It was using too much memory. That's a perfect example where basically the user is the long-term scheduler. Okay, so enough about that. All Are there any questions about what we've talked about so far? It's pretty straightforward, right? So let's start talking about these allocation policies because we have some interesting choices that most operating systems actually, again, beg off on, or they just punt, and they make simple choices that are much easier to reason about but aren't as cool. So basically, when we need a frame, we have two options. We could either take a frame from anybody that's running right now, excepting the kernel, of course, who's special. Okay, so basically, like I say, your process A causes a fault, and the OS is like, well, process A, you need another frame to load this page into that you wanted to refer to. And so process B looks like it's not using this frame right now. Maybe the corresponding page's access bit has been 0 for a long time. So let's go ahead and take the frame from process B and give it to process A. And so you see that the number of frames assigned to a particular process can change pretty dramatically over time based on who's causing faults. And so this is nice because the OS has a lot of flexibility as processes' memory requirements or their working set sizes change over time. We can give processes a lot of frames. We can take them away if processes are not referring to them, so that's kind of nice. But the problem here is that when one process starts to page fault, it can make everybody else start to page fault as well. So if everybody's working set sizes, again, grow larger than the number of available frames, then I have some serious problems. Okay? And so this is a bad thing. I can't identify the culprit anymore because unless, of course, you start noticing that process A has got like all the frames and other processes are like, I only need 3 frames, but I keep page faulting. Okay? So you could use that to tell who's being naughty. So global replacement is nice, and so most operating systems actually use global replacement because it is, it's really good at responding to processes dynamically changing resource needs. A local replacement policy is much more interesting because it keeps the fault rates localized to specific processes. So if I have a process that causes a fault and it needs a new frame, I take that frame from some other page that the same process is using. So now process A doesn't get to take from process B anymore. It's only allowed to take from its own set of frames. Now, you can see that if I have a local replacement policy, I need to be a lot more clever about how many frames I give to each process. With the global replacement policy, I don't have to be clever. Everybody can start out with 0 frames, and then as processes cause faults, I give them more frames. But in a local replacement policy, I have to be much more clever and say, okay, process A is using a lot of memory, so I need to give it more frames. So you can see that this is a little bit more challenging. Okay, so yeah, number of frames assigned to each process isn't as finely tuned. I have to now solve that problem. So you can see that a local replacement policy solves one problem and causes another. So this is why most OSs use global replacement. Okay. Let's see. So there's various ways that we can decide. So again, this is probably if you're dealing with local replacement as opposed to global replacement, because figuring out your page allocation, if you have a global replacement policy, who cares? You just let processes fault, and then you give them frames when they need them, and then you try to have some clever eviction policy that takes away frames that processes aren't using. At least that's what you hope. So page allocation policies need to be present if you have a local replacement policy. Okay, so let's say you have a total of m frames available to n processes. So you could say every process gets the same number of frames, okay, m over n. That seems okay, except obviously we all know that not all programs behave the same, especially as far as memory requirements are concerned. So what we could do is we could actually look at the virtual address spaces. Again, let's say on Linux you have your VM area struct list. You could easily go through and add up how many pages each process actually needs. And so we could say, well, let's try to do something a little bit more proportional. Like I say, our given process PI has virtual address space of size SI. I could just sum that up. You could use your supplemental page tables to add up how much virtual address space each process has, regardless of how many frames it's actually using. And then the sum of all process virtual memory sizes is this capital S thing, which is just the sum of all the individual processes' virtual address spaces. So then we could use that to proportionally allocate pages. I'm sorry, page frames. Okay? So if you say I need 1,000 pages, maybe you get 100 frames. And somebody says, I only need 500 pages, then you get 50 frames. Something like that. Okay? So again, you don't need this if you have a global replacement policy. But if you have a local replacement policy, these are the kinds of things you have to start thinking about. Okay, let's see, what else? Yeah, so again, we start thinking about, I start adding more processes. Now the virtual address space sizes are increasing, but the number of physical frames is the same, so each individual process gets fewer and fewer frames. And so this is sad. Yeah, so both of these actually exhibit this characteristic. So frames need to come from somewhere, and you can see that as we add processes to the system, if we have these kinds of allocation policies, the frames will come from other processes. And so you can see that over time we start generating more faults. And so this is where you could use medium-term scheduling to say, okay, I have too many processes, and I'm going to suspend some. And that should cause the fault rate to go down. And then when the fault rate has been down for a while, then you can start bringing up some suspended processes to increase the system load because it can handle it now. So those are some various details. Now, we already talked about working sets last time, so thankfully I don't have to reintroduce this idea. But the working set is basically, how should I say this? So the working set, as we all know, is the number of pages that I'm actively using. The presumption is that if I were to remove any pages in the working set from physical memory, I would quickly generate a fault. That's how we know that it's in the working set. Okay, so let's try to quantify the size of the working set and use that to assign frames to processes. Okay, and so as the program runs, its working set changes. I may have some pages enter and other pages leave. So there's certainly no guarantee that it's going to stay a particular size as the program executes. Okay? It is difficult to determine. Last time we talked about having a window, and we just look at the memory reference pattern or our approximation of the memory reference pattern by looking at accessed bits set by the MMU. And so we say if the access occurred within a particular window, then it's probably part of the working set. And then that gives you a chance to try to estimate what pages are in the working set. Now, if you take the aging policy, remember we had the aging policy where basically we had a regular interrupt, and we would look at all the pages access bits, and we'd put them as the high bit in some value, and then we shift all the other bits to the right, and the page with the highest value for its age would be a page that had been accessed recently, and pages that were accessed, if you had a set of pages that were accessed at a certain time or within a certain timer interrupt, the ones that were accessed more frequently would have a higher value than the ones that had been accessed less frequently, so that's kind of nice as well. Aging is a pretty clever policy. So we could do a similar thing for figuring out the working set. Except there's a couple of minor changes that we make. We have a B-bit value again, but now B is pretty small. Because what we're talking about, a working set changes a lot more slowly, so maybe we only do this scan every few seconds. So, and our B-bit value is much smaller. So B might be 4 or 8 or something like that. So we do the same thing as we did with aging. And we basically assume, since we're doing this on a less frequent interval, and we have a smaller number of bits, that if we have a page with a value of 0, that it is not part of the working set. Okay, so if it has a non-zero value, it's in the working set. If it's 0, then it's not in the working set. So basically, this is the idea. It's aging, but less sophisticated or less CPU intensive, and we could use that to do the working set model. Okay, so it's kind of fun. It's just like with your 4.4 BSD schedulers, how you would have your timer intervals, and on some timer ticks you would update some values, on other timer ticks you would update other values. You could do a similar thing if you built aging as your policy. then you could also, on some ticks, also try to estimate the working set of various processes. Okay, so this is the idea. And of course, using that, you can figure out what the degree of multiprogramming should be. So for example, you look at all your processes, you look at their working set age values, and you say, okay, this is the number of pages total that are in all processes working sets. That's 50 pages over the number of frames I have, so what I should do is suspend some processes. Okay? Or, hey, look, the working sets are much smaller than the number of available frames. I should unsuspend some processes. So it could do some things like that. And it turns out that this works really well. The only problem is that we don't have medium-term schedulers anymore, so we don't really do this kind of nifty, clever thing. And I would have a difficult time even thinking about how to incorporate this into a current end-user general-purpose operating system, because we don't really have large things that run in the background that we can just suspend and resume. Most of the things that people run interact with the user, so there's not really, you can't suspend it just because the system is overloaded. So this is partly why we don't have medium-term schedulers on general-purpose end-user operating systems. Okay? I don't even know if it would make sense to do this on servers unless you had some kind of background processing you were doing on a regular basis. But typically nowadays, that's even moved to a different server, so you don't even have that. Okay. Now, the other thing, like I say here, is that pre-paging, can't talk anymore. So pre-paging is another thing that is really helpful when you're unsuspending a process. If you already know what pages fall in that process's working set because you're keeping track of this stuff to build a medium-term scheduler, then why not just load all those pages for the process so that you don't generate faults when the process inevitably refers to those pages. Okay? So that's something that's a little side benefit of this kind of approach. So working set model is really cool. It's too bad that we don't have medium-term schedulers anymore. Otherwise, this is probably the kind of thing we'd be implementing in Pintos for your virtual memory assignment. Okay, any questions? All right, so that's enough about that. The other thing that you can actually look at is how often am I generating page faults? So like I say here, this is, the things that we talked about are really only most useful in the context of medium-term scheduling. So we don't really have medium-term schedulers, so what do we do instead? Well, we just look at how often page faults are occurring. Oh, I'm always dealing with page faults. This is bad, most operating systems have this kind of information. I don't know if anybody's actually accessed this information, but Linux has a way of reporting how many page faults process is generating and various other details like that, so that you can actually tell what your program is doing. And if the OS can return this to the user, then clearly the OS is also keeping track of these details. So, I'm seeing a lot of page faults. Maybe I need to assign more frames to a particular process. So you could always give it more frames in that situation. Now, the challenge with this is what I was mentioning before, that if you have a global replacement policy, then if one process starts faulting, it's going to cause everybody else to start faulting. That's kind of the issue that you run into. Because what happens is everybody's referring to the pages that they need, and the idea is that you don't have enough frames to hold everybody's working set, so the pager is not able to make good decisions anymore, if you think about it. Like I might see all of, if you had an aging policy, all of my pages have about the same age and they're all about the maximum age. Then I'm really sad. Or LRU, everything has been used really recently, so I can't really make good decisions. So in these situations with global replacement, the entire system kind of starts exhibiting this bad behavior, not just a single process. So this is where it's pretty bad. Of course, what you can do is you can say, well, how many, not just how many times is this process faulting, but how many pages does it have in memory, or what is its virtual memory size, or how many pages seem to be in its working set. And so clearly a process with a larger working set is a bigger culprit than one with a really small working set. So you can sometimes infer some details that way. Okay, so yeah, the pager tries to keep process page fault frequency within some range. The desirable range, now remember, desirable range is kind of a misnomer because the smaller this value is, the happier I am. The less time I'm wasting on interrupts and page faults, which are not doing real work. They're doing OS upkeep. So, but typically you say this range is okay. I can live with it. And if it gets above that range, then you start to get sad. And so the OS could go ahead and start assigning it frames. Okay, let me see what else we say here. So yeah, this all I think is very obvious and straightforward. Okay, so I have, again, if you can tell on a per process basis, if you actually see page fault rates, so this is below the thrashing level. If you see an individual process that's faulting a lot, give it more frames. If you see a process that's not faulting at all, take away some of its frames. And again, this makes the most sense in a local replacement policy context. If you have global replacement, you probably won't be able to use these strategies very well. Okay, let's see. Yeah, so again, this is another pitch for medium-term scheduling, clearly. Okay, let's see. So let's just wrap up. We don't have too many more slides, so this is good. We'll even end earlier than we expected to. But basically, like I mentioned, most operating systems don't have a sophisticated page allocation policy because we don't have medium-term schedulers. And if you don't have a medium-term scheduler, then there's no point in having a real sophisticated page allocation policy. You can't really infer very much from individual process behaviors. And so they just have some page replacement policy, global replacement, and they tend to use more aggressive page reclamation strategies, and they tend to have some kind of free page pool. Because remember, free page pools allow us to undo mistakes when I evict something that somebody's still using. Okay, so you basically let the user run the programs they want. So they are the medium-term scheduler. There is no OS built-in medium-term scheduler. If a process is blocked for a long time, well, guess what? If it's blocked, then it's not using its pages. So the pager is going to look and say, oh, look, these pages haven't been accessed for a while. I'm going to take them away. Okay? And eventually, if it remains blocked for a really long time, then all those pages will eventually be utilized by other processes. Well, that seems nice. That seems like a simple way of doing it, and it doesn't require a medium-term scheduler. I don't know if any of you have had this kind of experience where you will have something, like for me, it's typically PowerPoint or Word because I spend a lot of time in those programs, but I'll be writing an exam, and I hate writing exams, or I'll be writing a lecture, and they're okay. But, I'll not work on it for several days. And so the program is still running, but I haven't used it in a long time, and it's blocked on I/O. So all of its pages are now being utilized by other programs. And so, or I should say, the frames that its pages were occupying are being used by other programs. So then I go and click on it to switch back to it after like 3 days, and it takes like 4 or 5 seconds to restart because all the pages are being loaded from swap space. The pager is starting to reclaim frames from other places and load the data in so that the program can come back and start running again. So this is really common behavior for modern operating systems, and this is the reason why. This is the thing going on in the background. Okay, Linux. So very straightforward virtual memory policy. So we have demand paging. I'm so glad it's Friday. I can barely talk. So pages are never allocated to a process until they're used. So that's demand paging. So let's say that I decide I want to have a 100 megabyte allocation request to Malik, and Malik says sure. And none of those pages are touched yet. So when the program starts touching those pages, that's when I generate faults. That's when the OS actually sticks a frame there to handle the memory interaction. And only when it's evicted do I actually allocate swap space. And when I unevict it and pull it back into memory, the swap space is made available again, kind of like what you guys have to do for Pintos. So yeah, heap and stack pages aren't allocated to a process until it references the page. Okay, so yeah, that's demand zero paging for the heap and the stack. New name, right? So we have demand paging. Demand zero paging is just give me a page that I need, but it's not memory mapped. It's just set to 0. So this is where we say it's mapped to the anonymous file. The anonymous file only has zeros in it. So when you see like dev0 and so forth, these are the kinds of things that are, it's kind of the user exposed abstraction for these facilities. So Linux uses a modified form of the clock algorithm, interestingly enough, to maintain ages for processes, or processes pages. And so these pages are traversed periodically, and the ages will go up if they haven't been accessed in a while. And I'm sorry, it looks like they go down. So they decay to 0, and so if you have an age that's a high value, then it's been accessed a lot recently. Ages that are 0 haven't been accessed recently. And so then pages with a low age value will be reclaimed by the system. And it does this a little bit aggressively because it has a free page frame pool. And it will go ahead and pull pages back out if it is too aggressive. So it's a pretty clever approach. Windows is interesting because it allows programs to say, this is how many pages I want. So it can actually say, this is my working set size. But like I say, well, so Windows calls it the working set, but the resident set. Yeah, so this is kind of an important distinction. It's probably not that big a deal, except that probably the number one issue that I notice with students is that they don't understand the importance of the terms they're using. So I frequently hear people use page instead of frame, or things like that, and they don't really understand exactly what all the implications of these terms are. So, but in this case, the resident set is the number of pages the process has in physical memory. That may be larger than the working set. Because I may say, yeah, you know, I'd really love to have 1,000 frames, but the working set is only 40 frames. And so it's like, okay, well, sure, I guess I can give you all this extra space, even though they're not using it. So, of course, if a process says that its resident set is smaller than its actual working set, then the process is going to behave badly. Because Windows believes the process when it says, I need this many frames, and it's like, okay, that's how many frames. And if the working set is larger, then you'll actually get a lot of faults from that process. Now, processes do start out with a certain minimum and maximum working set size. You'll see it's kind of teeny tiny. I'm kind of hoping this has been changed in Windows 8 and Windows 10, but this is kind of the way that Windows operates. So default minimum working set size, or resident set, is really what we're talking about, is 50 pages, 200 kilobytes, hopefully is enough. 200 kilobytes should be enough for anyone. So, and the maximum is 345 pages, but the process can request a larger resident set. So there's various system calls that the process can make to say, you know what, I'd like to have a minimum of whatever, I'd like to have a maximum of whatever, and the OS will actually try to follow that. Okay, so Windows is kind of interesting in this way. So if Windows sees the overall system page fault rate go up too high, it has this really interesting mechanism called trimming, where it basically goes and tries to take pages, or I'm sorry, it tries to take frames out of everybody's resident sets. Okay. So what we're doing, remember, the resident set can fall in a range. So if it's toward the maximum, and clearly we can take some frames away before we hit the minimum, then we'll go ahead and do that. And so it starts going through and trimming. And basically it says, I need this many frames. Well, what it really does is it says, this is how many frames I need, so I'm going to try to get a few extra, because if the number of frames that the system requires is a little bit higher than that, by the time it finishes, then it's going to be sad. So it goes ahead and tries to go for more than it strictly requires. And so we have an aging policy again, which is interesting. Let me see. The most interesting part is this one, is that let's say that it hits its goal partway through this trimming process. Well, that wouldn't be fair to all the processes that didn't get trimmed. I don't know if the list is always in a particular order. So what it does is it just keeps going until it's covered all the processes, and it makes sure that this reclamation mechanism is fair. You know, everybody gets penalized the same. Okay, any questions? All right, so like I said, next time we'll try to start talking a little bit about virtual memory system implementation, probably have a bit of a question and answer as well. And then next Wednesday, we'll start talking about file systems and persistent storage. All right, we'll see you all.